Picking back up with the rest of Chapter 2, the Heisenberg uncertainty principle, from a guy named Heisenberg, I'm sure you've heard of him, states that it's impossible to simultaneously know both the speed and the position of a particle with any certainty. So we can't assign fixed paths. So when you see the picture of an atom that looks like this, it's still notoriously used, but this is when we said we knew, they had fixed orbitals, kind of like the planetary model of the atom. Before that we had the plum pudding model, all those, but the planetary model of the atom was much closer, except for the fact that we can't have these fixed paths. So where are the electrons? So we can't have those circular orbits that we saw in Bohr's model. So Bohr's model said that, we have the nucleus, then we have n equals 1, n equals 2, n equals 3, n equals 4, and he called them orbits. Well, guys, we're going to use the same idea, but we're not going to call them orbits. Instead, we're going to call them shells, because some work another scientist did named Schrödinger, which we'll talk about some more, came up with these very complex mathematical formulas to say where is the likelihood of finding an electron. So where is it most likely that we're going to find an electron? Where's the probability going to be the highest? And we call them shells. So we can't assign fixed paths to the electrons. They are, or circular orbits like we saw in Bohr's model, but we can find the probability of where they are, and then we can really never be sure that they're there at all. So remember, if we were talking about Bohr, he said that he thought an electron is allowed to occupy only certain orbits, so only specific energies, which we call now quantized energies, are allowed for these particular electrons. He didn't really know why, but he said an electron that's in any of these allowed orbits, remember he called them orbits, will not spiral into the nucleus. We're not going to get too far into this because we were thinking, okay, there's positive charge here in the center and negatively charged electrons here. Why aren't they attracted to one another? Well, they are attracted to one another, but they're not going to spiral into the nucleus because at the quantum level, things don't always happen the way they should. And we're not going to go too far into that. If you want to talk about that outside of class, we can do that. But we're not going to delve that deep into the quantum world of weirdness, okay? Radiation is going to be absorbed and released, though. We saw that picture, when you have our possible electron orbits here. If an electron absorbs energy and moves up, if it then must come back down, it's going to release energy, and that energy is going to have a value of some value h times nu. So when we drop to a lower energy level, we're going to release energy. These are those for hydrogen. So these are the different possible electron transitions for hydrogen. Only 4 of them, well, 5 of them technically, but 4 of them are in the visible region here. This black one we can't see, so it's just outside of our visual region. So when we were to do this in class, if we were to have done this lab in class, we would have been able to see these 4 lines when we looked at the hydrogen lamp. These are for hydrogen. Been able to see a purple, a blue, a green, and a pink. And you can actually calculate all of those transitions for hydrogen using the Rydberg equation. And we do that in lab. We're not going to do it in class because realistically it's just finding out where N1 is and N2 are, and then we're just going to be doing math with those numbers. It's can you plug numbers into an equation? And because there's squaring and some stuff, it is a little bit tougher, but we'll do it together. When we do it in lab, we'll practice a couple. But it's just really plugging them into an equation. So you can calculate all of the various transitions that are available to hydrogen. And hydrogen's special because Bohr did a lot of research with hydrogen, and so we have these names called the Lyman series, the Balmer series, the Paschen series, and the Brackett series. And while we can calculate all of these, we can't actually see all of them for ourselves. We can only see those 4 lines in the visible series here. Now, those would be the fingerprint identification, the line spectra for hydrogen. So Bohr assumed that the energy of a hydrogen atom is quantized, meaning it's coming in those small packets, right? We're still talking about that wave-particle duality where we have the wave properties and the particle properties, but what we're going to kind of focus on here is what does it mean to be quantized? So something that is quantized means that it has a specific value, and that specific value is limited. So, or it's limited to a specific value. So for example, it can be 2 and 4, but it can never be 3 or something like that. So that's just an example. If you've ever seen Quantum Leap, okay, Quantum Leap. If not, I recommend looking it up. I think you can see it on IMDb for free or by watching commercials. I watched it with my girls this summer. It was great. Blast from the past. So it's about string theory, and you have all these, string theories are your life folds back on itself, and you can quantumly jump from one point in your life to another point in your life. So that's a television program. If you're interested in that, it's kind of fun. Dr. Sam Beckett gets into a lot of shenanigans. All right, so back to this light little theory on quantum mechanics. So at any instant, the electrons can have one of several possible energies, but it can never be anywhere other than those. It can't be in between. So Bohr calculated what those energy levels were for the in his research. Excuse me, I'm tripping over my words today, and that is our quantum number n. I'm going to post this song just because it's an awesome, fun song, so you guys can listen to that at your own time. An electron in a hydrogen atom is normally found in its ground state. Well, guess what? That doesn't only occur for hydrogen. That's normal for all atoms, actually. And just like most of us on a lazy Saturday morning don't want to get out of bed, being in our ground state, we don't want to have to, interject energy to get out of bed. So if we don't want to go to an excited state. But this slide is just a really wordy slide that I got to fix about the difference between a ground state and excited state. A ground state is just when all the electrons occupy the lowest possible energy states. I am going to ask you for ground state electron configurations because otherwise, if I asked you for an excited state, you could write anything and it could be right. So I have got to be able to grade you on the fact, do you understand this? Do you know what's going on? So we're going to start with that diagonal rule, even though it's not always correct, especially when we get to the higher elements where there's a lot more electrons that have energy levels that are really close together. But I got to be able to grade you on something. So we're going to do this in the understanding that everything's going to be in its ground state when I'm going to ask you for ground state electron configurations. So sometimes, though, an electron is going to gain or absorb energy. And when it does that, it goes to an excited state. An excited state is anything above its ground state. Electrons in an excited state are unstable and they will fall back down to their ground state, and once it does so, it releases energy. So just so we're clear, when we gain energy, it's absorbing that energy, and when we fall back down, we're losing and releasing that energy. Unfortunately, Bohr's model only works for hydrogen. Oh, sorry, Bohr. But electrons do not travel in circular orbits like we said. This is, I still buy my girls' t-shirts with that atom marking on it because I want them to have nerdy t-shirts. But it's not technically correct because we would have to have something with shells and not orbits. But we do have two concepts that still appear in modern theory, which are the principal energy levels and the principal quantum number n. So let's talk about those. Quantum mechanics. So Schrodinger had a cat. Yes, Schrodinger did have a cat, but he also came up with some very, very complex mathematical equations for the possible energy states of an electron. So where can these electrons be? You see this, which looks like a fuzzy little blob? It's a fuzzy little blob in two different areas that indicate every single dot indicates a probability of where the electron can be. So this is a probability electron diagram that shows where the electrons could potentially be. But we don't ever know that they're there, and we have no way of proving it because Heisenberg said we can't both at the same time know the speed and the location of the particle. So the energy states of these wave functions are characterized by a set of quantum numbers. So this tells us the energy state. There are 4 quantum numbers. I'm going to do Qn for quantum numbers. So instead of referring to them as orbits now, we're going to refer to them as atomic orbitals. So different, huh? All right, so they are different because in each atomic orbital, They are where the electrons probably found, not this is where they are. So what happened was Schrodinger made these equations, put these equations together to bring both the wave and the particle characteristics together into a wave function. So quantum numbers are required to describe the distribution of electron density in an atom. I like to call it the electron's address in layman's terms. So every electron in the atom has a 4-digit address. 3 of those digits describe the house it lives in, which is the atomic orbital. So there are 4 quantum numbers. These three are required to describe the atomic orbital. And that's going to be the house it lives in. And then it's a duplex. So is it apartment A or apartment B? And apartment A will be 1 electron via the plus 1/2 spin, and apartment B will be the second electron that has a minus 1/2 spin. So I'm obviously putting this in layman's terms. There are 3 quantum numbers that describe the atomic orbital. They are n, which tells me the size of the orbital, L, which tells me the shape of the orbital, and m sub L, which tells me what direction does it face in 3-dimensional space. So the orientation in 3-dimensional space. So the principal quantum number n, and this is going to be very redundant because I find in class redundancy is necessary sometimes, but maybe online this will be a little bit different, and I apologize. I probably need to go through and fix up these slides. Not probably, I do. So n designates the size. So you're going to need to be able to tell me what all of these quantum numbers do, and then we're going to be able to go back and forth from a condensed version of these numbers to telling me about what it means, okay? The larger the value of n corresponds to a larger size. This is intuitive. There's nothing tricky about it. The values must be integral numbers, 1, 2, 3. In fact, our numbers are going to be 1, 2, 3, 4, 5, 6, and 7, just like the 7 periods on the periodic table. And what's cool right now in this day and age is our 7th period is now full. So are we working on an 8th row of the periodic table? The value of n corresponds to the value of n in Bohr's model. So it's really the same, it's just the distance from the nucleus, but now we're calling it atomic orbital instead of an orbit. Now, terminology, you need to know what this means. You must have the terminology down or you cannot answer the question because you won't know what's being asked of you. So a shell has the same value of n. Well, that might not mean anything right now, but when we get to row 3, we're going to see there are 3s, 3p, and 3d. This is the 3 shell, or n equals 3. All right, so all of these have the same n value because they all have a 3 out front. That is the same shell. Angular momentum quantum number, L, it's usually this cursive L unless I go and something happens with the font, but it describes the shape of the orbital. Right now we have 4 different shaped orbitals that are not theoretical. So we have these are known, but theoretically there are many more. H, I, okay, etc. But we're going to focus on the known and not the theoretical, okay? So don't worry about anything other than S, P, D, or F. So you don't have to worry about theoretical, only the known. You do need to know that when L is equal to 0, we have an s orbital. When L is equal to 1, we have a p orbital. When L is equal to 2, we have a d orbital. And when L is equal to 3, we have an f orbital. So if I showed you on that last slide that we have 3s, 3p, and 3d, I'm going to show you what each of these look like individually. Depending on when this is, we've already discussed a lot of this in class, but I'm going to talk about the different shapes and how many different ways that they can face in three-dimensional space. But S is a sphere, and watch my sphere, it's so terrible. All right, so if I were to do this and this, okay, and then, yeah, okay, looks more like a pumpkin. But if this is my sphere, how many different ways can a three-dimensional sphere face in 3 dimensions? Because spheres, by definition, are 3D. We can only have one way, right? One direction, not the band. Okay, but p orbitals are dumbbell shaped. So if we were to have, this is y, x, z, just because, pick whatever you want. This would be py, px, and pz. So there are 3 different directions. In D, there are 5, and when we get to the F, eventually, there's no 3F, but there will be 7. So a subshell, instead of listing PX, PY, and PZ all the time, because that's a little bit more in depth than we're going to have to go as far as knowing which exact orbital these electrons are going into, you'll cover that in an advanced inorganic class when you get that far, or a little bit further down the line. For right now, we're going to say that all of these, if they are in 3p, they're in the 3p subshell. Okay, so 3p subshell or sublevel. So the definition of a sublevel is something that has the same value of N and L. And I'm just going to highlight that for you in the notes. So a subshell has the same value of N and L. You know, this is kind of one of those lectures that makes a lot more sense once we get it all in. So let's just keep moving on. So if L is equal to 0, we have an S. If L is equal to 1, we have a P. If L is equal to 2, you have D, and L is equal to 3, you have F. You are going to want to be able to write just really quickly S, P, D, F, 0, 1, 2, 3. Just to remind yourself when you go to take the test, it's not something that's going to be given to you. It's something you're going to just have to know. So again, sublevel or subshell is a specific level that's identified by both the same principal quantum number, L. Hold on. Okay, a specific sublevel is identified by both the principal energy level and the, I don't know. Let's just get rid of that. I don't even know. I have to fix that. So a sublevel has the same value for the principal energy level, N, and the angular momentum quantum number, L, okay? The total number of sublevels within a given principal level is equal to N. So if I have, let's see, one, and it's going to be more clear on the next slide. I probably should just move forward, but how many sublevels can I have in N equals 1? 1 sublevel. In 2, and that one's 1s, by the way. In 2, there should be 2. 2s, 2p. In 3, 3s, 3p, 3d, although the 3d actually is in level 4, where it's energy-wise. 4s, 4p, 4D, and 4F. Now, after that, we technically have 5S, 5P, 5D, 5F, and I believe the next one is 5H. I don't know, but that's theoretical, and we don't need to know that. So you're only going to need to know up to 4 for filling and identifying. Anything after that is going to be theoretical. So this is what this slide says. In n equals 1, there is 1s. In n equals 2, there is 2s and 2p. N equals 3, 3s, 3p, 3d. N equals 4, 4s, 4p, 4d, 4f. And anything after that, we do add more. So while these values of n are very important for as far as energy goes, we're going to talk about how when the orbitals get larger and the energies come closer together, the energy isn't always only looking at this number. But when we do look at that number, it does matter. So if I'm going to look at a sublevel, excuse me, if I'm going to look at a shell, I better start using the words correctly, right? So within this shell, this is the 4th shell, okay, 4s is going to be less energy than 4p, which is less than 4d, which is less than 4f. So energetically, S, P, D, F, always within the same shell. Now, effective nuclear charge. I know we've mentioned this before, but I'm going to mention it now and tell you what it is and tell you about it. So I've just like briefly mentioned that, and you don't have to go back and find it or anything. But Z is the nuclear charge. So when we were talking about what's in the nucleus, this is what is the charge in the nucleus, essentially. The number of protons, right? So the number of protons in the nucleus of an atom, which is Z. Same Z we talked about before. Z effective is the actual magnitude, how much of the positive charge is going to be experienced or felt. We use those layman's terms to give people like qualities to these electrons. I know it annoys some of you, but that's okay. By an electron in an atom. So depending on where the electron is, it's going to feel a different pull from the nucleus because of all the other electrons in there. So Z effective is going to be the actual Z, the number of protons, minus this shielding constant. And this is sigma. Sigma is the shielding constant. Now Z effective is going to increase as we go across the periodic table. It's going to increase. It doesn't change that much as you go down, but it does increase, but it's not as significant as when we go across, and we're going to talk about why. It doesn't change very little. It does change. It goes up, as we go down the periodic table, but it's going to change as we go across because these electrons are going to be having the same shielding constant, but we're adding more electrons to that same sublevel. Or actually that same shell, I should say. Sublevel, then shell. So what is shielding? Shielding is what happens when an electron has, okay, so if we have a nucleus here, and we have, this one has electrons in it. 1, 2, 3, 4, 5, 6, 7, 8. And we're talking about an electron out here. These other electrons in this area are going to shield this electron from feeling that full force of the nucleus. So 8, 9, 10, 11. This would be sodium, I guess. Sodium, not sodium plus. It's just a habit, I guess. So it would shield it a bit by these inside electrons. Now, other electrons in the same shell, if we were to say, okay, now it's magnesium, because we put another electron in there, this electron isn't going to feel that shielding constant is going to remain the same, but now we're changing the pull of the nucleus because of how many electrons we have on the outside. So the number of electrons is going to become important when we talk about this. I'm going to make this much more clear. I'm sorry, I'm kind of stumbling here. I'm trying to think about something different or do something different that I normally do. Okay, so I'll just keep going. Occurs when we have many electrons, and so we're shielding that positive charge. So we're not getting that full positive charge, just like you don't get the full cold if you wear a coat. Okay, it's fall, we're starting to put coats on. If it's winter, you hopefully have a coat on. you know, we're not going to feel as cold because we have a coat on. So we're shielding ourselves from the cold. Same thing. So core electrons, the ones that are full, I just erased that, but those are the ones that are in shells that are full, are going to be the inner electrons. Those are going to shield the most, and they're constant as we go across the period. That's what I was trying to demonstrate, but I should have waited. So as we go across the period, Z goes up. So shielding effect is just describing that balance between the pull of the protons on the valence electrons and the repulsive forces from our inner core electrons. So let's take a look. Lithium should have a Z of 3 because it has 3 protons. But the effective nuclear charge, the charge felt by the valence electron, is 1.28. Beryllium 4, effective 1.91, and so on. We can see it increasing, but what we see here, nitrogen 7 is 3.83. So when we see this, we see the effective nuclear charge increase. This is actually one of the explanations for a lot of our trends that we see on the periodic table. So the shielding effect actually explains why valence shell electrons are more easily removed from an atom. This is where our bonding is going to come from, is from those valence electrons. But it also explains the atomic size. So as we go from lithium to nitrogen, even though we're adding more electrons, and we would think it's going to get bigger, it's not going to get bigger because it's going to actually pull tighter because we have more electrons in the same shell, and they are going to actually decrease in size. And we're going to talk more about this when we talk about trends, but it has a lot to do with the effective nuclear charge. So effective nuclear charge, what is it? It's the net positive charge that's experienced by valence electrons. And you can calculate it by taking Z and take Z effective is equal to Z minus the shielding constant. Okay? Now, we're not going to have to calculate this. If you are, I'll give you the shielding constant. But I do need you to understand what it is because we're going to be able to explain a lot of our trends with this. So every sublevel has a certain number of orbitals. S has 1 orbital. So these are orbitals versus a sublevel. Okay? Sublevel has orbitals. Orbitals, sublevel, shell. Okay. A P has 3 orbitals. A D has 5 orbitals. And an F has 7 orbitals. On the periodic table, it's going to be my hand-drawn, awesome version of a periodic table here. Oh, that shouldn't be that high. I really probably should just put one in here. Yeah, we'll do this. I'll fix it in the end. Yeah, we know that I'm not a good drawer, right? Okay, it's hand-drawn periodic table. Woot woot. Got it. We would say this is the S block. This is the P block. This is the D block. And this is the F block. Now, up here we have hydrogen, and helium we know is over here, but for electron configuration purposes, helium really should be there. So just for electron configuration purposes, the reason the helium is above group 8 is because even though it only has 2 electrons, where the ones above group 8 have, the ones in group 8 have 8 electrons, is valence electrons, excuse me, is because it acts like a noble gas. Its valence shell is full because it only has an s orbital. So the s block is, let's talk about that. An s block is 2 elements wide. There is 1 s orbital, right? 1 sphere. Each orbital can hold 2 electrons. So the s block one s orbital can hold 2 electrons. Hydrogen is 1 electron. Helium has 2 electrons. Check. Then we would go down to the next one, which is lithium and beryllium. This has another electron. This has the second electron. So I'm just actually going to put a 1 here so we don't. So this would be 1, 2, 3, 4. Then we go over to the P. This is 6 elements wide. So a P block has 6 elements in it because it has 3 orbitals, each holding 2 electrons for a total of 6 electrons. The D block is 10 elements wide for a total of 5 orbitals, each 2 electrons, total 10 electrons. F block is 14 elements wide, 7 orbitals, each with 2 electrons is 14 electrons total. And that might be a little bit too much information, but this is when you forget how many s orbitals there are, you can count the width of the block and divide by 2. When you forget how many p orbitals there are, you can count the width of the block and divide by 2. 6 divided by 2 is 3. There are 3 orbitals. Same with D and same with F. The magnetic quantum number, m sub L, is going to describe the orientation. So this is where we're going to get more in depth on what am I talking about when I say 1 orbital, 3 orbitals, 5 orbitals, 7 orbitals. What am I talking about? So m sub L describes the orientation of the orbit in 3D space. So we're talking about 3-dimensional space here. So we're talking, px, py, pz, whatever order you want to put these in, just label them, right? Doesn't matter. You're not going to have to draw this for me. I keep getting worse every time I try to draw it. All right, but it goes from negative L to positive L, and don't forget 0 in the middle. The values are always integer values, and they depend on the angular momentum, so they depend on L. So what is L? L for S, P, D, and F is 0, 1, 2, or 3. So if I have an s orbital, it's equal to 0. If I have an s orbital, let's just do this over here. So s is equal to 0. How many different ways can I do that? Well, negative 0 to positive 0 is just 0, so one orbital. P is equal to 1. Negative 1, 0, and 1. 3 orbitals. And I drew those out for you before. I'll show you them on another slide here in a moment. I'll attempt to make it a little bit more clear. So Py Px and Pz. So Py, oh, wrong button. Px and Pz. Three orbitals. D is 2, negative 2, negative 1, 0, 1, or 2. 5 orbitals. I'm not going to draw those here for you. I think I have a picture of them, but I can draw those ones. I can't draw f orbitals. I'm not that talented. Is equal to 3. -3, -2, -1, 0, 1, 2, or 3. 7 orbitals. Each holds 2 electrons for a total of 14 electrons, 10 electrons, 6 electrons, and 2 electrons. So this is another way of looking at it. This is the 0, L equals 0, L equals 1, L equals 2, L equals 3. So we can see what happens, and then we have, this is our L values here. These are our N values. The first time we get D is in N equals 3. The first time we get F are in N equals 4, and so on. So what happens to our fourth quantum number? Well, our fourth quantum number is the spin. Which way is it spinning? Is it spinning clockwise or counterclockwise? So there's 2 possible directions. I like to say that clockwise is +1/2 and counterclockwise is -1/2, but it honestly does not matter in this case in what we're doing here. So all that's going to matter is if we have, let's say, 2p, an energy diagram here. So if we have orbitals that are degenerate, meaning they're all the same energy, if we put these in there, if I draw an electron, it'll look like that, and this negative electron will look like that. Whichever way we do it, as long as they're all the same direction when we do it first, that's what matters. So when you put them in, as long as you put them in all facing the same direction, when then you pair them later on, that's what matters. And you just need to know that the values are +1/2 or -1/2. Those are the 2 possibilities. So Schrödinger derived these mathematical equations. He took both the wave and the particle characteristics of electrons into consideration and came up with a wave function. The wave function squared is giving us these electron density maps. You luckily do not have to do these calculations until much further in your inorganic career if you choose to do so. And hopefully you have enough hair to pull out by the time you get there, unless you really, really love math. But why is it darker towards the center here? Because it's going to be more likely to find an electron closer to the positively charged nucleus than it is farther away from the positively charged nucleus. So what we're going to see as we go is it's more likely to find an electron near the nucleus than it is to find it farther away. The electron density diagrams show us that, but these representations just allow us to say where we think the electron is, and probability density decreases as you increase the distance from the nucleus, is what I'm saying. Let's look at these maps. So this is the radius here. So from A to R is going to, as we increase this distance towards R, we're going to decrease the probability. So this looks like this in a graph. So this is the wave function squared of the distance R. And this is one of those things that, it approaches a 0. It approaches 0. Never mind that. So what we see is a spike in probability, the spike here, and then we see it approach 0, and this would be considered a node, an area where it's very unlikely to find an electron, almost 0 possibility. As we go out and we get, these are s orbitals, we're going to see a spike happen, so this would be 1s. Then we see a node. Then we see another spike. This is 2s, and then a node. And then we see another spike. This is 3s, and then a node. So we see areas of high probability and then no probability, or little to no probability, and then another high probability. 1s is smaller than 2s, which is smaller than 3s. And in this case, what we're looking at is these dark areas here in the middle are going to show us our area of probability. The white area is little to no probability. That's a node. So 2s, this is the principal quantum number, is 2. S tells me the angular momentum quantum number is 0. And then m sub L, which is the what number? Magnetic quantum number. The only possibility is 0 because it's a sphere. And this could have a 1 here, meaning there's 1 electron in that orbital. Or it could have a 2 there, saying that there's 2 electrons in that orbital. But that is the maximum that we can have in an s orbital. All right, so moving on. These are the p orbitals. This is what I've been attempting to draw for you in so much prettier picture. So we can have three possibilities for L, from L being 1. There, m sub L is equal to -1, 0, or 1. I am not going to even tell you and not specifically assign which of these is -1, 0, or 1. Again, that's something you'll discuss when you get to a higher level in organic class. D orbitals, aren't they pretty? I can draw these ones. I can't draw the F, but these are the D orbitals. There are 5 different possibilities in 3-dimensional space. Isn't DZ squared just kind of fun? It's got the little donut in the middle. When L is equal to 2, we have m sub L of -2, -1, 0, 1, or 2. So 5 possibilities, each holding 2 electrons, can give us a maximum of 10 electrons in the D block. And then I don't have the F on there, so let's go back for F. The shape is a double. Actually, no, it's not. It's a quadruple dumbbell for the most part. Like these are a double. And they're really difficult for me to draw, so I'm not going to draw them. I thought I had pictures of them, but I must not have. So when L is equal to 3, m sub L can then be equal to -3, -2, -1, 0, 1, 2, or 3. So we have a possibility of 7 orbitals and 14 total electrons. So let's summarize quantum numbers. Principal quantum number tells us the size, angular tells us the shape, and magnetic tells us the orientation in 3-dimensional space. All 3 of these describe the house the electron lives in, the orbital it lives in, the atomic orbital, right? The last one describes the electron, m sub s, and it tells me which way it spins. So this is being specific. You will not have to be that specific. This is just for an example. So this is 2px. What would the quantum numbers be? N would be 2. L would be 1. Oh, my arrow needs to point that way, sorry. And px, in this case, is just picking one, would be related to the magnetic quantum number. So if I asked you what are the quantum numbers here, you could say n is equal to 2, L is equal to 1, and m sub L, you could pick one, or you could say -1, 0, or 1. All of those are possible. Then we have the spin quantum number. So the electron spin, which way is it going? Well, it could spin clockwise or counterclockwise, and it's going to be +1/2 or -1/2. So plus or -1/2 is usually fine for m sub s.